In this lecture, we talk about binary trees. Binary trees are a special case of graphs, which are a generalized representation of collection of objects which are interrelated. Whenever a collection of objects are related among themselves in some sense, that can be modeled using graph. Mathematically, a graph can be represented as a pair consisting of vertices and edges, objects and relationships. So a graph can be represented as a pair V comma E, where V represents a set of vertices and E represents the edges among the vertices. Here V cannot be empty, so I can't call it as a graph if there are no vertices at all. But a graph can have vertices but no edges at all. That is called a null graph. That's a special case. So V cannot be empty, E can be empty. Now in this example, we have a graph here A, B, C, D consisting of 4 vertices, and they are connected through edges. AB is an edge, AC is an edge, BC is an edge, like BD and DC are the edges. This is how we can construct a graph. And a special case of a graph is called a connected graph. A graph is said to be connected graph if every vertex is reachable through a path from the given vertex to any other vertex. Path in the sense a collection of consecutive edges can be treated as a path. So if every vertex is reachable from the other through a path, we call it as a connected graph. Similarly, we can describe a cycle if there are a collection of edges starting from a vertex. If we can tracing through edges, if we can reach back to the given vertex, then it forms a cycle. So in this case, AB, BC, CA is a cycle forming 3 edges, consisting of 3 edges. So that's a cycle actually. Now again, a special case of the graph is said to be a acyclic graph. A graph which do not contain even a single cycle is called an acyclic graph. So there should not be any cycles. Similarly, we can describe the concepts of degree of a vertex as number of edges incident on the vertex. We call it a degree. So in the given graph, degree of A is 2, degree of B is 3, like that degree of C is 3 and degree of D is 2. So these are all the terminology that we use in the graphs. Now, a special case of a graph is a tree, where a tree is a special graph which is acyclic and connected. So a connected acyclic graph is called a tree. So what do you mean by that? Connected in the sense every vertex should be reachable from the other through a path, and acyclic means there should not be any cycles in the graph. So in the example here, A, B, C, D, 4 vertices are there, but there are no cycles, and every vertex can be reachable from the other. So such a graph is called a tree. It's a special graph which is called a tree. And a collection of trees is called a forest. Of course, here we deal with trees only. Graphs can be represented in the form of multiple linked lists, where each node may consist of the data, and depending on the number of children or number of nodes that are connected to that vertex, links can be maintained in each of the nodes. So here is an example of representation of a graph with different nodes. Binary tree is a special case of tree where the number of children at every node is restricted to at most 2. So at every node there may not be a child at all, 0 children, or 1 child, or at the most 2 children. If there are 2 children, we call it as the left child and right child, and there can be a left child but there is no right child, or there can be right child and there is no left child, or there may not be a child at all. The starting node is called the root node, and the left part of the root node is called the left subtree, and the right part of the root node is called the right subtree. Interesting feature of binary trees is that at every node we can have the left subtree and right subtree. So it's a self-similarity can be observed in terms of the subtrees. Similarly, when it comes to the representation of the binary trees, there is a concept called level order index. To indicate this, we can have the levels for the binary tree. Starting with the root node, it is called the level 1, and the nodes that are connected to the root node are called the level 2, and subsequent levels we can describe in terms of level 3, level 4, and level 5, like that. As the level grows, the number of vertices at that level grows in powers of 2. Now, the level order index can be defined as index for the root node is given as level order index is 1, and the right child will have 2 times of the parent node plus 1, so 2 plus 1, 3, and the left child will have 2 times of the parent node, 2 into 1 is 2. So like this, at every stage, the level order index of a vertex can be defined as 2 times of the parent node for the left child and 2 times of the parent node plus 1 as the right child. So in this example, we have the binary tree having A, B, C, D, E, F, G, H. We can observe the level order indices. Level order index of the root node is A is 1, level order index of B is 2, level order index of C is 3, D 4, E 5, F 6, G 7, and H 8. Again, a special case of this binary tree is a complete binary tree, where given if there are n number of nodes in the binary tree, if the level order indices are all the numbers are there from 1 to n, we call it as a complete binary tree. And again, another special case is full binary tree, where at every level all possible vertices shall be present. For example, if I take level 2, there should be 2 vertices. Level 3 should have 4 vertices, and level 4 should have 8 vertices. Like this, at every stage, if complete set of vertices are there at that level, we call it as a full binary tree. The advantages of binary tree lies in the representation itself, because we can simply represent the binary trees with a double linked list. Root node can be depicted, A can be depicted with a double linked list, data consisting of A, and the left link and right link can be saved in the link part of the node. Like this, at every stage, we can have a representation of the binary tree in terms of double linked lists. Now, another concept is height. Height of a binary tree can be defined as length of the longest path from the root to any of the leaves can be taken as the height of the tree. And arrays can also be used to represent binary trees once we have the level order indices. So based on the level order indices, we can insert the elements of the binary tree in the array in the corresponding level order index locations of the array. So in this case, in this example, if you observe, A is occupied in the place 1 because level order index of A is 1, B is 2, C is 3, D is 4. There is no vertex with level order index 5, so 5 is kept empty. So in future, there may be a possibility of inserting a vertex at level order index 5, so that is kept empty. 6 and 7, 8 are occupied with F, G, and H. So like this, we can also have a array representation for a binary tree in terms of level order indices. Given a binary tree, if data represented in the form of a binary tree, the first task is to read the data from the binary tree. It is called the traversing through the binary tree. This can be achieved in 3 ways, either in-order traversal, pre-order traversal, and post-order traversal. The in-order traversal can be described as visit the left side of the node, visit the node, and visit the right side of the node in the sequence. That means, given a node, first go to the left side of the left subtree of the node, and then after the completion of the left subtree, visit this node, and after that go to visit the right subtree of the node. This is the sequence in which we traverse. When it comes to the algorithm, you can have a recursive type of algorithm here, calling a function on its own. In-order traversal of the node, if node is null, then it has to be stopped there itself. So if node is not equal to null, then we call again the in-order traversal function on the left child of the node. And then once the left child is complete, traversal is complete, then we visit the node and print the value of the data of the node. And then once that is done, we go to visit the right subtree. So again we'll perform the in-order traversal on the right child of the node. So this being a recursive program or recursive algorithm, it traverses through the nodes. Here is an example. Given this binary tree consisting of A, B, C, D, F, G, if we start with the in-order traversal at A, immediately it calls for the in-order traversal of left child of A, B. Again, B at B, again this is a subtree. It being a tree on its own, it can be treated as a tree on its own. If we start the in-order traversal at B, it calls again the function of in-order traversal of left child of B is D. Again, it calls the in-order traversal of H. So at H, again it calls the in-order traversal on the left child of H, it is null. So again the in-order traversal of H is complete. Then visit the node at H. So print H or visit the node H. Then call the in-order traversal on the right subtree of H, so which is again null. So this completes the in-order traversal of H, so that the in-order traversal of left child of D is complete. Then visit the node D for that in-order traversal of D. Then go to the right child or right subtree of D, in-order traversal of right subtree of D, that is null. So this completes the in-order traversal of left subtree of B. Then visit the node B. Then go to the right subtree of B, null. So this completes the left subtree of A, and visit the node A, go to the right subtree. So like this, the sequence in which we visit the vertices is starting at A, left subtree B, come to B, left subtree of B is D, again left subtree of D is H. So print H, print D, print B, print A, then go to the right subtree C, again go to the left subtree of C, F. So there are no left and right subtrees of F, so print F, then print C, print G. This is a sequence in which we traverse. Another variant of traversal is pre-order traversal, where node will be visited first and then left subtree followed by right subtree of the node. So algorithm follows like this: pre-order traversal of the node. If node is not equal to null, then print the data present at the node and then proceed to the pre-order traversal of the left child of node. After that, proceed to pre-order traversal of right child of node. So if we trace this again, starting at A, perform the pre-order traversal at A. So first we print the node, because visit the node is done. Print node A, then call the pre-order traversal on B. Again print B, call the pre-order traversal on D. Print D, call the pre-order traversal on H. Print H, again call the pre-order traversal on the left child of H. No, null. So come out of this, complete. Then go to the right child of H. No, null. That is complete. So for the pre-order traversal of B, node is visited, left subtree is over, there is no right subtree. So at B, pre-order traversal is complete, and at D, there is no right child, so pre-order traversal at D is complete, and at A, the node is visited and left subtree of A is over, then go to the right subtree of A. C, again at C, visit the node C, print C, go to the left subtree of C, F, print F, no left subtree, no right subtree, F is complete, and in-order traversal of C, left subtree and node is over, so go to the right subtree of C, G, so print G. So the sequence in which the vertices are visited is A, B, D, H, and then C, F, G. The third alternative is post-order traversal of the tree. Here we'll visit the left subtree and then followed by right subtree, and at the end we observe the node or read the data at the node. So again the algorithm goes like this: post-order traversal at the node is if node not equal to null, then proceed to post-order traversal of the left child of the node, and then proceed to the post-order traversal of the right child of the node, and then print the node or visit the node at the end. So if we traverse this again, post-order traversal on A, go to the left subtree, left child, post-order traversal on B, go to the left child, post-order traversal of D, post-order traversal of H. So post-order traversal of H at H, there is no left subtree, there is no right subtree, so directly we print the H, data H. The once that is done, the left is post order traversal at D is over, so there is no right subtree, so print D. There is no right subtree at B, print B, and left subtree of A is over, so immediately we'll go to the right subtree of A, C. Again go to the left subtree of C, F. At F, no left subtree, no right subtree, print F. Then left subtree of C is over, go to the right subtree of C. At G, no left subtree, no right subtree, print G, and then print C, and then this completes the left and right subtrees of A, print A at the end. So the sequence in which the vertices are visited is H, D, B, right, F, G, C, A. One of the applications of binary trees is representation of the mathematical expressions in the form of a binary tree can be done. To represent this, what we do is each leaf node can be taken as an operand and non-leaf node as an operator. Again, we will follow the precedence among the operators. The standard precedence order applies. So brackets first, and then division and multiplication are the next priority, and then followed by plus and subtraction. We'll follow this to represent the expression. As an example, if we observe the mathematical expression given here, the brackets comes first. Within brackets again, the innermost bracket consisting of expression consisting of b power 2 minus 4 multiplied with a e. So exponentiation comes first, so b power 2 shall be represented as b and 2 are represented as leaf nodes, followed by exponentiation as the parent node of those two, and then 4 AE or 4 and A are multiplied first, so 4 and A are leaf nodes, multiplication is done, and then it is multiplied with E, the output is multiplied with E, so multiplication, output of this to E, and then subtraction of these two expressions, subtraction of these two is done at the parent level, and this completes the innermost bracket. Then followed by exponentiation with 5, so 5 is taken as a leaf node and one more parent level is added with exponentiation. That completes the operation inside the bracket. Multiplied with minus b, so minus is a unary operator here, so minus is directly operated on b, which is again multiplied with the output of the previously constructed subtree. So multiplication of this minus b with the subtree is done with multiplication as a parent node. And followed by division, again there is a bracket, so 2 multiplied with a is done again with multiplication as a parent node for 2 comma a, and ultimately division as a parent node for the entire expression of these two. So like this we can represent the mathematical expressions in the form of a binary trees. The advantage is that we know how to traverse the binary trees, so we can represent these expressions in terms of in-order traversal, pre-order traversal, and post-order traversal.